So the output stage we also did already do. Yeah, we already designed a simple CS output stage, but now I would like to go, because of the efficiency, to a balanced output stage, a complementary parallel CS stage. That is what I would like to have as an output stage here for this amplifier. And also here we have to ask ourselves, what is the influence of the feedback capacitance? Oh, there's noise performance, sorry. That should be on the load drive capability. And also here it is as if it is in parallel with the load. Not in parallel with the source for the noise, but for the load, for the voltage and current drive capability, it appears in parallel with the load. So the question is, can we design a push-pull stage that can drive 100 ohm in parallel with the feedback capacitance, and that was 2.5 PF at 30 megahertz. Well, 2.5 PF at 30 megahertz isn't that low impedance, so it doesn't really cost a lot of current budget. But it's important that you realize that this feedback capacitance also needs current. So there's the output stage also given in a file, of course not in SlideCap, because SlideCap is intended for linear simulations, so you won't see any clipping, and that is what we are looking for now. We want to see the clipping. So these are the values that I found to be, let's say, valid. 40 micrometers with M is 11 for the P and M equals 3 for so that's the multiplication factor. So basically you have 440 micrometer for the P FET and 120 micrometer for the N FET with an operating current of about 1 milliamp. And this is the circuit that I used. I just tuned the voltage V1 to such a level that that I don't see any crossover, and I still have class AB operation. So this is also done in LT-Spice, and since LT-Spice has everything open, it is this one. And here I have a transient analysis putting something on it, but there's nothing here. Advanced sine. Oh, that was just for doing the operating current, but I would like to show you the sine wave. So let's just put some amplitude, like I think it was like 250 milli. That was enough to drive the stage. We want to go at the highest frequency and run the simulation. And where's my output stage? Here. And see the output voltage. And you see it clips at 350 millivolt, and the upper one and the lower one is about symmetrical. It's there's a little bit offset, but that is all not of important. The only thing we want to know now is, can we drive the load? And yes, we can drive up to 350 millivolt, which means that it is good enough, because we need 320 if you use the crest factor of a sine wave, and that is what we assume for this exercise. So basically here you see this is the result. So with these numbers we have a good starting point for the design of the output stage. And of course you can do higher currents, making the width larger, but there's no showstopper here in the process that we cannot drive it from within the power supply. I just do 250 millivolts peak at the input, which is not outside the range of the power supply. So it's 500 millivolts peak to peak, and I obtain the correct output value. So this is the circuit, and we found the values, and the values that have been, oh, sorry, the values were listed on the previous sheet here. So 40 micrometers and 11 times and 3 times for the P and the MN respectively, and 1 milliamp quiescent current. That would do. And why do I need that? Because I want to design the whole signal path, and I want to go to a two-stage design.